Alright, so we're still in Chapter 8 working on trig substitution. Now, if you try to go back to your original arcsines and arccosines, it looks like arcsecant, except for the fact that I've got this 2 here. Now, arcsecant doesn't have an x squared in that form. And you could try to do u substitution, like u equals the inside du. I don't have a 2x dx on the top. So, and I can't distribute into the square root. That's just something that we can't do. So let's get rid of that. That's just bad. So it looks like a trig problem. It looks like an arcsine or arccosine. That's one of the giveaways that we're going to use a trig substitution. So, and even if you've forgotten your normal ones, you can do this on any arcsines and arccosines. Now, the positive part, whatever's positive, is my hypotenuse. So my hypotenuse is x. I'm going to make my easy side be on my close side. And then, oh, this shouldn't be 4 because it's x squared minus 2 squared. That's how I get 4. And then my missing side is my x squared minus 4. So the triangle is sometimes the hard part, but that's the main idea here. So we need an x squared term, and then we also need the square root. Well, the square root's the easy one to draw. My square root's the opposite, and I want to avoid the x when I'm trying to write an expression for the square root. So I'm going to use my opposite and my adjacent, which is tangent. So tangent of theta is my opposite, which is the root, x squared minus 4 over my adjacent, which is 2. Now the goal was to get an expression for the x squared minus 4, so we multiply by the 2 to get that out of there. So that cancels, and I get my x squared minus 4, or my square root of that, to be, quite simply, 2 tangent of theta. So that's my expression that I'm going to plug in. So I've got 2 tan theta on the bottom. But right now I got to figure out how to write x squared, and I need something for dx. So we go back to our picture, and the key is we got to use x. Well, I don't want to use the opposite, so I've got to do my adjacent, my hypotenuse. So I'm looking at cosine of theta is my adjacent, which is 2 over my hypotenuse, which is x. So it's kind of a pain because x is on the bottom, so x is going to be 2 over cosine, or 2 secant of theta. So x squared is going to be 2 secant squared theta. And then dx is going to be 2, well, derivative of secant is secant tangent. Derivative of tangent is secant squared. So that's what goes up for dx. Secant theta tangent of theta. And I got a 2 here. So a couple of 2's cancel. The tangent cancels. One of the secants cancels. So I know it looked really crazy there for a second, but all I have is 1/2. I have a d theta on top because I technically, whenever I have dx, I'm going to have d theta at the end. So I should have my d theta here at the end. And I've got a secant left on the bottom. So if I've got a secant left on the bottom, when it flips to the top, it becomes cosine. So the antiderivative of cosine is sine. So we got this 1/2. Sine of theta plus c. Now I can't just leave it as sine of theta. So what I have to do is I have to figure out what sine of theta is. Well, go back to my triangle. Sine is opposite over hypotenuse. So we have 1/2, the opposite, which is our root x squared minus 4 over hypotenuse, which is just x, plus c. So the last step is actually pretty easy when you have a sine or a cosine left over. You just go back to your triangle and figure out what sine or cosine is. So hard part is drawing the triangle and figuring out what it is. So our steps: draw your triangle, the positive is always hypotenuse, and then you've got to come up with expressions for everything in your problem. You need one for your square root here, you need one for your x squared term, and you need one for your dx. Once you've got them all, you plug them in the right spot. Dx goes for dx, x squared for x squared, and our square root, wherever the square root is. From there, you cancel out, see what you have left, and hopefully you can do your antiderivative.